Greetings, everybody. So I want to talk about this problem which I have found on our assignment. And it says use change of variables or the table to evaluate this definite integral. Okay, so first thing I do is it does mention this table, and there are tables of general formulas that you can use when they're appropriate. And so I might be kind of curious to see what that is, but when I click on it, nothing here is useful to me at all in this problem. These are all trig functions of various kinds, none of which relate to this purely algebraic function. Okay, but I can't really control if that shows up in the problem or not, but it is there. I looked at it, it's not useful, so I have to think of some other way to solve this. Now, when I start solving a definite integral like this, what I think about is the fundamental theorem of calculus. And in order to use that, I need to find the antiderivative of this function that's given to me, which is x divided by the third root of x squared minus 2. Okay, so when I see that, I think that with a little rewriting, it becomes pretty obvious that a u substitution would work. Okay, so in other words, the rewriting is that I see this in the denominator as x squared minus 2 to the 1/3 power, and I can write it in the numerator as x squared minus 2 to the negative 1/3 power. In looking at that, I see that if I let u be x squared minus 2, the du that I also have to substitute will involve the x dx. So I can fully substitute u in terms of x in this integral, okay? Or sorry, x in terms of u. So here's how I would get that substitution to work. So I'll let u be x squared minus 2, which is this, okay? As a consequence of that, du will be 2x dx. All right, so that's how we apply u substitution. And I'm not going to explain a whole lot about that part of it because I've made other videos to introduce how u substitution is done. All right, so this is not intended for you to be the first video you watch on u substitution. So I choose the u, I get the du is 2x dx, but see right there, I don't have 2x dx. The goal is to substitute the x away and get u instead. And if that said 2x dx, then I would substitute du, but that's not what it says. So I treat this like an algebraic equation. I divide both sides by 2, and I get that x dx, which is what I have there, is du over 2. So it's between these that I can fully substitute away the x. All right, if I make that substitution as indicated in this original integral, then I'll get the antiderivative, the indefinite integral of u to the negative 1/3 times du over 2. That over 2 is a factor of 1/2, which I'll factor out. Now, the reason I wanted to get to this part right here, as I believe that I could, is that there's a very basic, straightforward formula for getting the antiderivative of u to the negative 1/3 du. Okay? And it's that you do this. You add 1 to the power and you divide by that same number. It's that simple. So what I start with is something fairly complex. The substitution makes it about as simple as they get. All right. So here's my antiderivative of u to the negative 1/3 du. It's u to the 2/3 over 2/3. I still have this factor of 1/2. And if I take 1/2 and I multiply by 3/2, which is what that turns out to be, I'll get 3/4 u to the 2/3 power plus c. Okay. Now, at this point, I'll notice that my original integral was in terms of x. I substituted in u to make it easier to work. And it did that for me. I accomplished it. I was able to solve it through the substitution. But I'll take this tactic of getting my original variable back. Okay, so how do I get the x back? It's through the substitution. If u is x squared minus 2 and I've got u right there, then here's my final answer. The antiderivative in terms of x 3/4 times x squared minus 2 to the 2/3 power plus c. Okay, so that's my antiderivative. The antiderivative of this original function, the one that you see given in this problem, the antiderivative of that is 3/4 x squared minus 2 to the 2/3 plus c. Okay, so that's my first step. Because I wanted to use the fundamental theorem of calculus to solve this original integral in the first place, and I just need the antiderivative to do that. So now I have it, and here's how the fundamental theorem of calculus would look. I take my antiderivative with my lower and upper bounds of integration. I put the upper bound into the antiderivative first, I subtract, and I put the lower bound in, and I calculate, okay? And I notice that this says round to the nearest thousandth. So when I calculated this, I get 6.680762. So rounding that to the nearest thousandth, I'll get 6.681. Okay, and I'm done. All right, now a few comments about this, and here they are. First comment is, whenever I give you the general antiderivative of anything, I put this plus c there, okay? And the reason for that is this. For me to say this is the antiderivative of this original function is to say that if I took the derivative of this, I would get that. And that's true. You can use the chain rule and take the derivative of this and show that you get this original function, proving that you have the correct antiderivative. But because the derivative of any constant is 0, then truly to be the antiderivative, we'd have to say 3/4 x squared minus 2 to the 2/3 power plus any number. The c could be anything. Plus 12, that could be the antiderivative. Plus 25, that could be the antiderivative. There's no way to know what the c should be, though, in general, so we just put plus c, okay? So that's why that's there. Why don't I incorporate that into this definite integral by the fundamental theorem of calculus? Why didn't I put 3/4 x squared minus 2 to the 2/3 power plus c? Well, I could have, and what would happen is the c would cancel out every single time. So we just can leave it out. And the fundamental theorem of calculus says you can use any antiderivative, all right? And if I leave the c off, that's one of them. If I thought this was that the c was 12, 3/4 x squared minus 2, 2/3 power plus 12, and I could put that in there, the 12 would cancel, okay? So that's why we just leave out the c altogether in definite integrals when we use the fundamental theorem of calculus. So, all right, that was a little bit rambling, but I feel like I should address it because here I have plus c because I have the general antiderivative, but when I used it over here, I left it out. That's why, okay? Next thing is this. I notice if I do view an example, it gives me this right here. And even if I don't read that too closely, it makes it seem like once you substitute the x away and get u instead, you could adjust the bounds to be in terms of u also. That's what that seems to say, and that is what it says, okay? So, in other words, I did not have to use the substitution for u, solve it, and get the antiderivative, and then substitute x back. I could have avoided that last step, and here's what I mean, okay? So I posed this question to you to address what was in that help feature on my math lab. After the substitution, do we have to convert from u back to x? And the answer is no, you just have to adjust the bounds if you don't. So I started with this integral. And lower bound was 2, upper bound was 6, but I guess implied in that is that the x is 2 and the x is 6 for the bounds. It's the x that's 2 and 6. If I decide to work this integral in terms of u because it'd be easier, that's fine, but I'll adjust those bounds. So we'll do like this. If x is 2, and if you're working with the substitution that x squared minus 2 is this other variable u, then what's u? So if x is 2, 2 squared is 4 minus 2 is 2. So that lower bound, if you put it in terms of u, would be 2. The upper bound, all right, if x is 6 and if u is x squared minus 2, well, 6 squared is 36 minus 2 is 34. So if you want to, you can take your original problem, decide on a substitution, but change the variables and the bounds from x to u by way of that substitution. So that would get me this. And what was that, when I had that problem, when I was working it, what was that antiderivative that I found in terms of u? It was 3/4 u to the 2/3. So I can just use that with these bounds and get the same answer, rather than take my antiderivative in terms of u, then convert back to x and use that. Now, I don't think it makes a big difference either way. I mean, we get the same answer. And I don't really think one's easier than the other. But if you happen to read something like that as the advice for how to solve this, or the instructions, then I would say yes, that would work. But it also works if you just change back to the original variable. So I would leave that up to you. All right. But I say that, I spend the extra time in the video to mention it because I think that's the advice that you'll see if you watch other videos, if you look on my Math Lab for the help features, if you look in a textbook. But I hope this shows you it works fine either way.